So here we are in the second video cast of Chapter 16, and in this series we'll take a look at sections 16.3 and 16.4, and we'll look at the relative strength of acids and bases, and then give them a rating scale. The rating scale will involve the amount of hydrogen and hydroxide ion, and then we'll look at the P scales associated with those. So first, let's start with a little chemistry in your everyday life. And let's take a look at the structures that we were looking at the beginning of last video cast called amino acids. And we learned that amino acids have an amine group right here that can act as a base, and a carboxylic acid group right here that can act as an acid. And I gave you two examples of some of the simplest amino acids right here, glycine and alanine. And we learned last video cast that bases are proton acceptors, and so one of the things that amino acids do is that when they exist in large amounts, which they always do because they never exist as single molecules, they can react with themselves, and this hydrogen can be given away to this other end of the molecule right here, which is the basic end. And when it does that, then it self acts as a acid-base reaction, and this end now is lacking a hydrogen, and this end now has a hydrogen, and it has more of a positive end here and more of a negative end right here. It forms an ion by itself, giving up the hydrogen here and adding a hydrogen right here. Experimentally, you might want to know, well, does it actually exist like this, or does it actually exist like this in solution or in a crystalline solid? And when you look at amino acids in solid form, many times they form solids as ions with some anion or cation that's attached to it. And they have higher melting points, acting a little more like ionic solids, making this act more like a polyatomic ion. These ions have a fancy name. These are called Zwitter ions, with a positive end here and a negative end here. So, proton donors, proton acceptors, let's take a look at that, and let's look at the relative strengths of all different kinds of acids and bases. So we're continuing in section 16.2 if you're using the 13th or an edition of the Brown and Lake textbook. And the relative strengths of acids and bases are illustrated by defining acids or base as strong or weak. When something is a strong electrolyte, we learned back in chapter 4, it means that it completely dissociates or completely ionizes or completely breaks up into positives and negatives. The stronger the acid, the more it wants to break up and form H pluses and whatever the anion is. And then the anion, what's left over after the acid is released as a proton, is very, very weak because it does not want to join back and become that strong acid. For example, HCl in the solution forms H pluses and Cl minuses. This is the conjugate base of that acid, and it's not a very strong base at all. As a matter of fact, it's super, super, super weak. Some people say it's neutral, and it has no affinity to grab a hydrogen and then become HCl again. It does not want to do that at all. And so the stronger the acid, the weaker the conjugate base. Conversely, the stronger the base, the weaker the conjugate acid. And so hydroxide, for example, in NaOH, would form Na pluses and then OH minuses, and OH minus would be really, really good at getting hydrogen ions, and so it would react with waters in solution, and then it would take a hydrogen away and form HOH. But HOH doesn't act a whole lot like an acid anymore. It doesn't want to give away hydrogens a lot and then become OH minuses. Not very much, and so it has a much weaker conjugate acid. Let's take a look in your textbook. They rank a number of acids and bases, and this is in figure 16.4. I'm just going to zoom in on this a little bit so you can see it a tiny bit better. And you can see a ranking scale of different acids and bases, and you can see that these have strong acids up here that you memorized, like hyperhickel high, honohickel low. And then you can see some strong bases down here that contain OHs. You can see lots of weak acids in here, acetic acid, carbonic acid, and then some pieces from phosphoric acid. And even after one hydrogen is given away, it still acts acidic, but it's weaker. Another hydrogen is given away, but it acts weaker. And then you can see where water ranks. And then you can see some things that have negligible acidity, like OH minus. It doesn't want to give away another hydrogen. H2 and CH4, they have no affinity to give away hydrogens at all. They're just too stable. And then over here on the base side, you can see the weak bases here. Ammonia, you probably know. Some anions right here are good weak bases because they're good at getting hydrogens. And then you can see some super strong bases, some things right here that just really will grab hydrogens really fast. And these are similar or on the same area as those hydroxide containing things. It's just that these aren't stable at all. They'll grab a hydrogen. These won't exist in solution anymore. These guys right here, these strong ones and these strong ones right here, immediately either grab a hydrogen in these case or break up in these case, causing something called the leveling effect inside of the solution. So let's go back to the notes. And on page 677, they outline three things that identify strong acids and strong bases. So rule number one is that strong acids completely dissociate or ionize in solution. They split up, and therefore they don't exist as something like HCl aqueous. They only exist as H plus and Cl minus. Rule number two is that weak acids or therefore weak bases, they only slightly ionize. Or slightly break up. So something like HF, that one will have two arrows and only makes a few H pluses and only a few F minuses. And we'll give a ranking scale to that soon. And then rule number three is the things with negligible acidity. These ones are like CH4. They're super stable molecules, don't give away hydrogens at all. Like H2, they don't break up, they don't ionize, they don't act as an acid or a base in solution. So let's take a look at some lists and see if we can rank these. Let's see if we can arrange these from the strongest, from the weakest to the strongest acid. So we've got H2SO4, we've got HOH, H3PO4, HPO4 2 minus, H3O plus, and then CH4. So I can identify right now one super weak thing in there, something that doesn't want to act as an acid or a base, and it's very stable. We just talked about it as something with negligible acidity, and it has no tendency to give up H+. And so we're going to rank these from the weakest to the strongest down here, down this way. So this one has no tendency to give up hydrogens at all, and so it would be the weakest, so cross that guy off the list. Let's see, this one we know is a strong acid. This one's got 3 hydrogens to give away. This one's got 1 hydrogen to give away, so it's not going to be very strong. This one's pretty strong acid too, but our next strongest in this area would be probably this H2SO4. But just a little bit about this CH4. So just an aside, if it would be lacking a hydrogen and be CH3, it would be like one of the strongest, super strongest bases there are, because it really, really wants to get back to this neutral compound, or this neutral species, this neutral molecule, and get H pluses a lot. So the next weakest would probably be our water. Water can act as an acid or a base, as we'll see a lot during this chapter. And so it's not very strong at all. It just has to be influenced by something, but it could be an acid or a base. And so those two are crossed off. And so of the remaining species, this is super strong. This is going to be really strong. And then between these two, whenever something has more hydrogens, it's going to be stronger. Whenever something has more hydrogens, it's going to be stronger versus something that has less hydrogens that's the same type of species. And if you look at this, this would be like a conjugate, actually a double conjugate of H3PO4. So HPO4 minus 2 would be the next strongest acid. And then after that would be H3PO4, because that's a weak acid, as opposed to these two guys right here. H3O plus is the strongest acid that can exist in equilibrium in an aqueous solution. And then the one that wants to be the very strongest and break up right away, immediately upon hitting water, would be H2SO4, which we memorized as one of the 7 strong acids. So let's focus a little bit closer on this species right here, because as I just identified it, I said it could act as an acid or a base in water, and it actually does that, and it actually forms ions even a little bit by itself. And we call this the auto-ionization of water. The auto-ionization of water means that water will react a tiny bit by itself and form some H3O plus and some OH minus. Not a lot, but a tiny bit. And we could write a K expression, or an equilibrium constant expression, for this reaction, where we take the products and divide it by the reactants and put it to the power of its coefficients. But remember, reactants or products that are pure liquids or solids aren't in the K expression. And when we do this, as long as it's at 25 degrees Celsius, we get 1 times 10 to the negative 14th. And at 25 degrees Celsius, this equilibrium constant has a special name. It's called Kw, or Kdub. Kw for water, of course. So you can see in this figure right here, they give several different examples. Here's a hydrochloric acid. I'm sorry, here's an acidic solution, and you can see that H plus is much greater than OH minus, but our H plus times our OH minus always equals 10 to the negative 14th. A neutral solution, those two are equal to each other, but H plus times OH minus is 10 to the negative 14th. And in a basic solution, you can see that OH minus is much greater than H plus, but our H plus times our OH minus is always equal to 10 to the negative 14th. And so this equation always is super helpful to us, because if we know one, we can find the other. And so our mathematical portion, almost the end of this video cast, calculate the OH minus if the H plus is 5 times 10 to the negative 5th. So our equation Kw says that H plus times OH minus is equal to 1 times 10 to the negative 14th. And so we take H plus and we put it in for we take 5 times 10 to the negative fifth and put it in for H plus, and then OH minus would be X, or the thing that we want to find. Solve for X by dividing by both sides, and we end up with 0.2 times 10 to the negative 9th, or 2 times 10 to the negative 8th molar for OH minus. So if you know one, you can find the other due to the autoionization of water and the way that these two species react in all aqueous solutions.